multiplication of the wire elements, and there is this e to the power of something,
and that's a twist.
Yeah, because by associativity it gives you a cosine.
Yes.
If you write the associativity.
And that's all you mean.
That's all I mean. So that's a twisted version of a well, it's a closed-cycle twist of a Hopf algebra, which is placed by this group algebra.
Actually,
and then you get projective representation because it's a twisted group.
Yes, and then you have to go and lift them up.
And lift
like in
multipliers.
Like in the case of metaplectic representations in ordinary quantum mechanics. Exactly in the same way. Yeah, that's true.
Okay.
It's links up directly.
So, my name's Nick Monk, University of Sheffield. I think the idea is we all do a kind of potted version of where we're coming from and our background and why we're interested in quantum theory. So, I actually work on modelling developing embryos, which this is a fruit fly embryo, Drosophila and Askloster. So this is the outline of the embryo early on. And this is a very
Sorry, embryo what?
The embryo of a fruit fly.
Ah, fruit
fly. So each of these bright dots is one of the nuclei. So at this stage, the fertilized egg cell is the nucleus of that cell is divided many times, but there are no cell membranes. So it's a single cell with lots and lots of nuclei in it. And these different colours are expressions of different proteins at these stages. So I'm going to very briefly at the end talk about biology, because I thought you might not want a whole talk on biology. But where I actually came from was that I did my PhD with Basil a number of years ago now, shall we say, looking at algebraic representations of intricate order in the context of quantum theory, and in particular the idea of the notions of pre-space and pre-geometry, and whether you can actually get space and time out of the process itself rather than imposing them in some way and then having things happen on a space-time background. And the reason I will come back to embryos at the end of this, so after my PhD I moved into biology. One of the main reasons being, well I should say the main reason is money of course. It's a lot easier to get money to work on biological systems than philosophy of quantum mechanics, as I'm sure you all know. But the real reason, not really money of course, I wouldn't be so mercenary, was because I was interested in the origins of order and descriptions of order in natural processes or in natural philosophy, if you want to call it that. And biology is really, to my mind, the richest source of notions about order and pattern that we can draw upon. And I think we're reaching an interesting stage certainly in developmental biology now, embryonic development, where we're starting to understand enough about the mechanisms that we can actually start to get some interesting insights into the origins of order in developing embryos. It's something that I know lots of people have talked about in the past in a more or less abstract way, because we didn't really know anything about the mechanism of embryonic development. It's always been very mysterious because we really didn't have the data like we have for physics. And so it's been talked about, certainly David Bowen talked about the intricate order in the context of the developing seeds. We were talking about this at lunchtime in a rather strange way. Excuse for misunderstanding. So I know it's been talked about before, but I think that we're reaching the stage now where we're beginning to know enough about the mechanism that in the next few years we might actually start getting some interesting insights into more general questions of the development of order and pattern from a biological context rather than a physical context. And that's what I've always hoped to do, is to bring these two streams together, because I was looking at order and process in quantum theory, where you have the mechanism, certainly in terms of the mathematical structures, which is what we've heard a lot about already today and we'll hear a lot more about in this meeting. So we've got all the structures there, and what we're trying to see is, do those structures actually tell us something interesting about where order and pattern and how we can understand order and pattern and where they're coming from? And I felt that maybe quantum mechanics was a bit limiting for the general issue of studying intricate order and process and various things like that. So my hope is that biology will bring us something into that more general area in the reasonably near future. Now we're learning more about mechanism. Anyway, so I'm not going to talk about biology mainly today, and then go back to physics for a short time. So just to give a little outline, I should apologise because, as I've said, I'm really a biologist now, so I'm not going to give a very mathematical talk, which maybe some people are relieved about after we've had some hard maths today. So this is kind of light entertainment at the end of the day. I'm really going to just talk about general issues, just hopefully raise some issues that will be amplified during the rest of the meeting in a more mathematical context. And I'm going to focus on the general issue. I don't think everybody knows about pre-geometry. The idea that rather than having a geometric or a space-time structure in at the start of our theory, we actually have some mathematical representation of process from which space and time emerge, and as well as entities and objects in interaction and things like that. So I'm just going to really outline these ideas, and then I'll have a look. So Basil's already nicely given a description of the algebraic representation process or intricate order, so I'm not really going to say a lot about that because Basil's already done that. And then I'll look at the Weyl algebra again. I don't think this was planned, that the Weyl algebra will come up in every talk today, but I will also take a very simplistic look at the Weyl algebra to give a toy model for how you can start to get space-time structures out of an algebraic representation of process. And it really is a toy model. I'm not proposing here that we're really getting space-time out in any realistic sense, but just to give an idea of what the approach would be if we can really take an algebraic or any mathematical representation of the intricate order to the ultimate conclusion that we would like of having a process from which we get everything out. So this I think we're all probably very familiar with. Conventional is a dangerous word to use, but I'm going to use it anyway. What do we mean by a conventional approach to space-time in physics? Then we essentially have dualistic theories, certainly traditionally in physics, that you have some given space-time background that you're assuming, and then what you do is that you assume that you have some kind of individually existing entities. Talk about these IEEs, which are things, particles, or whatever. In physics we normally think about particles, it could be fields, but they're things that we can give some well-defined autonomous properties to, more or less accurately. We know what we mean by it. We talk about an electron, we talk about a photon, we talk about various things. The fact that we can give it a name, that there's a noun for it, means that it has some well-defined properties that are autonomous to it. And so what we have is this space-time background, and then these entities which certainly interact with each other. That's the dynamics of our theory, and in certain theories they may even interact with the space-time structure, so most notably general relativity, where the individually existing entities actually affect the space-time structure on which they move, and their dynamics are defined. So I'm not saying that these two have to be independent of each other, but nonetheless, even in general relativity, there is still a well-defined space-time and a set of well-defined entities which interact on it. And these are distinct things, really. And the mathematical formulation, conventionally, as we know, is that the space-time background is represented by some differentiable manifold with metric on it. And then typically, we have a set of differential equations representing the dynamics with the time derivative giving us rates of change on top of this manifold. It's a very conventional approach to this. Referred to this background, this space-time background that we have with its differentiable manifold and metric, then all these theories assume two basic properties that, and Basil again mentioned these, so that was stolen the last my thunder in this.
No, come on, you go on.